solve the eigenproblem, solve the eigenvalue and eigenvector of a matrix. Okay. So these are very computationally intensive calculations. Okay. And yeah, if the matrix is getting very large, okay, and the lab pad mostly for the dense matrix. That means most of the elements of the matrix are non-zero. Okay. There are other matrix called the sparse matrix. Sparse matrix is usually very large, and only a few, not too many elements, okay, are non-zero. Okay, so these are sparse matrix. In science and engineering also, we encounter a lot of the sparse matrix. But for the sparse matrix, we cannot use the lab pad to solve the eigenproblem or to obtain the solution of a very large set of equations. Okay. So for the lab pad, okay, mostly addressed to the dense matrix. Okay. And MAGMA is the GPU accelerated lab pad. Okay. Yeah. And I will give two examples of how to call the lab pad and also how to call the MAGMA. Okay. Yeah. One is the eigenproblem of U and symmetric matrix. Okay. Yeah. Another one is the eigenproblem of a Hermitian matrix. So these two problems are mostly common encountered in physics applications. So, for example, for solve the Laplace operator on or the Schrödinger equation, a particle in a box, and also a chain of the mass spring systems with fixed ends. Okay, so these are the examples. Okay, I can call the routine. Okay, DSYEVD or GHEEVD. Okay, to solve the problem, the eigenproblem. Okay. And also for the momentum operator on the one-dimensional lattice, and that is the Hermitian matrix. So I can use the GHEEVD, okay, to solve the eigenproblem. Okay. Yeah. So the lab pad, okay, originally was actually the first version, the very first version was written in Fortran 77. And the latest version is written in Fortran 90. Okay, and yeah, they provide the routines for solving systems of simultaneous linear equations. Okay, or we call a system of linear equations, and also many other related problems. Say, for example, least square solution. Okay, yeah, that means you may have more equations than the unknowns. Okay, then in that case, then you only have to solve the instead of the matrix, you can only solve the A deca A. Okay, yeah, and in order, yeah, so the solution is called the least square solution of a linear system. Okay, and also the eigenproblems and also the singularity decomposition. Okay. So there are only many matrix operations, okay, related to a system, a matrix, okay, yeah, which can be used, yeah, for the lab pad. Lab pad can solve all these systems, but they are mostly for dense and band matrices, okay, and not general sparse matrices. Okay. Yeah, in all these routines, it provides the real and complex matrix, okay, and single position and double positions, okay. So this is similar to the brass, okay. Yeah. So if you look at the first letter of the routine, then you know, okay, what kind of data type it handles. Okay. Yeah. So lab pad written such that as much as possible of the computation can call the brass, okay, yeah, and yeah, mostly they will exploit the level 3 brass, okay. So that is the matrix operation, okay, matrix modification, and so on, okay, yeah. Yeah, that you can also call the lab hack with the C or C++, okay. And I refer you to this link, okay. It gives you a detailed prescription how to do it, okay. So you have a C code, and then you use the lab hack, okay. Then yeah, then you can use the prescription, okay, given here in this link, okay, to do it. For the Magma, okay, it is a GPU accelerated lab hack. Okay. So the Magma actually is the abbreviation of the matrix algebra on GPU and multi-core architectures. So it actually make use of the not only the GPU but also all the CPUs. Okay, yeah, all different kinds of architecture. Okay, are taken into account. Okay, so yeah, actually that is a Magma is the design implemented by the team. Okay, develop the lab pack and the scale pack. Okay, and yeah, so yeah, it allows the applications, okay, to fully exploit the power of the current systems of multi or many core CPUs and multi GPUs. Okay, yeah, so you don't have to worry about how what was the system. Okay, yeah, what kind of system. Okay, yeah, you can have the many CPUs and also many GPUs, and then Magma suppose, okay, can take advantage all the all the available resources of the system. Okay. Yeah, but I don't know to what extent, okay, the optimization is done, okay, because it's a kind of not this is the underlying design of the Magma. Okay. Yeah. So, and they keep on updating the version, give an updated version, and then get a better performance. Okay. So, so there, yeah, here I only focus on this Magma DSYEVD. Okay. So this is for solve the eigen problem of the view and symmetric matrix. And this is the routine for solving the eigen problem of Hermitian matrix. Okay. And these two kind of problem are mostly common in physics, I think. So let me first talk about the eigen problem of the view and symmetric matrix. Okay. So so this is the header file has to be included. Okay. And then I have to initialize the Magma. Okay, Magma init. Okay. And then I have to allocate the space, okay, for the eigenvalue and also the eigenvector. Okay. So for the eigenvalue, I have the n, okay, and then the size, okay, is n. W1 is to have the size array of size n, okay. For if this matrix is n by n, okay, and for the eigenvector is n squared, okay, yeah. So, and then first I have to query for the workspace sizes, okay. So you have to call the Magma routine, okay, in order to get the workspace size, okay. So this is the L work and I work, okay, and then so Magma allocate, okay, this at the CPU of such a memory space, okay, yeah. So this is the memory for the workspace, okay. And then after that, okay, then I proceed to compute the eigenvalues and eigenvector. Okay? So call this routine, okay. Yeah, you see the magma wet and the magma lower, okay. All this has to be same is here, okay. Yeah, after we yeah, yeah, get the query for the workspace, okay, for the, yeah. So this is the how this routine is called, okay. And finally, okay, you have to finalize the magma, okay. Yeah. Actually, this all these prescriptions, okay, how to call this routine, okay, yeah, it's different in this in the cookbook, okay, yeah. So this book, okay, yeah, as I told you last time, this example, okay, the examples of the calling the yeah, the Kubas and then the magma, okay. So yeah, this so this matrix computation on the GPU, okay, Kubas, Kusolve, and then the magma, okay, yeah. So magma is the yeah, implemented, okay, by the by a group of applied mathematicians in University of Tennessee, okay, yeah. And the Kubas and Kusolve actually yeah, also implemented by the same team, okay, yeah. So so you can just look at these examples, and then you can know how to call these routines explicitly. Okay, for example, this is matrix modification SGMM. Okay, then it has the yeah. Okay. And for other case, for other routines, then you can just look up okay from the uh, content, okay, or index, okay. Yeah, yeah. I'm not sure it has the index at the end. Okay, let me check. Okay. No, it doesn't. Okay, so all you can get is at the in the fund. Yeah. So the content here. Okay. So from the contents, okay, then you can look up which routine you need, and then you can go to it, and then yeah, yeah. This cookbook already a few years old, okay. And you see, this is the back in 2017, okay, 7 years old, okay. So I think, okay, there's some new routines, okay, which has not been included in this notebook, in this cookbook, okay. Yeah. Then you have to find out somewhere if you need to use this latest routines, then you have to get it somewhere in the web, on the web, okay. Yeah. So let me back to the yeah. Okay. So let me go to the code, okay. Yeah. Yeah, there's a because the magma, okay, for the CUDA, okay, latest version CUDA 12.3, okay, yeah, it, it still need to be compiled, okay, in order to work, okay. So, yeah, it's still being compiled, okay. So after it will be complete, the whole library is compiled, then I can call it, okay. Yeah, so I cannot run the code to give you a demonstration, okay. Yeah, but I can show you the source code, and then the source code, okay. The sample code should work, okay, but just do not submit a job, okay, to be run by the latest version of CUDA, okay.
Excuse me, may I
Yes,
ask some question
yes,
here?
yes,
Just to understand the terms shown in this slides better. So I'm
yeah,
still understanding why the abbreviation appeared like a DSYEBD, while I can guess that SY probably stands for symmetric,
yeah.
and the EV is like an eigenvalue. But what does the D
D,
mean?
here the first letter D, okay, actually
Mhm.
stands for the double precision, okay, view, okay, view double precision, okay, yeah,
Okay.
okay.
How about the second D in the word?
You mean the last D, okay?
Yes.
Uh, I don't, I I think yeah, symmetric matrix, okay, eigenvalue, yeah,
Uh-huh.
this D, okay, I think is a kind of yeah. Let me look at the all the naming routine, okay? You see, yeah,
Uh-huh.
here, let me see. Let me go to this, okay. You see, these routines are uh, naming convention, okay, is according to the lab pack, okay, what is in the lab pack, okay.
Uh-huh. Uh-huh.
So it's not due to the magma. Magma is just you see all the magma code has the magma, okay, in front of it, okay. So
Yes.
the original name, okay, actually is from the uh, lab pack, okay. So uh, yeah, let me first identify the code DE. Uh, this is single position, okay. So I have to go to the uh, okay, okay, okay.
Mm-hmm. Mm-hmm.
So this is the routine, okay, yeah. Uh,
Double precision.
so it's not quite clear, okay, what's this last the name, okay, the meaning of I mean the convention, okay, yeah. So symmetric eigenvalue, okay, problem, okay, but then why there's an extra D, okay,
Mm-hmm.
yeah, that is the kind of the theme of the actually this name, okay, naming convention was originally, okay, from this IcePad, okay, eigenvalue package, okay, IcePad. Um, yeah, I think it must have is some vision, okay, but just now is mostly ignored, okay, yeah.
Mm-hmm.
So we just look up which routine and what is its function, okay, and the name, okay, yeah, we really don't uh, really, yeah, want to know exactly what it was the operation for, okay,
Mm-hmm.
so yeah,
Okay.
so
Mm.
all this letter, the first letter I know is a double precision. Okay, SY I guess is symmetric. Okay, eigenvalue. Okay, D maybe there's a reason for that. Okay, I don't know. Okay.
Mm-hmm. Okay. I have one more question. Just
Yes.
on right this page. So here I see magma lower and the magma upper, but what does that mean in this
Which
routine?
let's see. So you are seeing my slide here, right?
Yes, exactly.
Yeah. This is the magma wet and magma lower. Okay. Yeah, it's kind of the magma routine. Okay, kind of. This is the yeah some
You see, like
information, okay, obtained here, and then this information has to be passed over here, okay. Yeah, actually, yeah, I have to look up the menu, okay. You see you have to look up here, okay. You know, yeah.
On the same page.
First parameter, okay. You see, the first parameter can take the values of this, okay, or this, okay. So you see the symmetric matrix A, okay, can be stored in the lower of this or upper of this, okay. So here is in the, because it's symmetric matrix, okay. So I only need to store half of the elements, okay, diagonal and also a lower or diagonal and also all upper elements, right? Because it's a symmetric matrix. So this is only storage space, okay, for this lower triangular matrix, okay. Yeah. So this is called the lower, okay. Yeah, magma just because it's the magma, okay. Yeah.
Okay, so
Okay.
we are kind of decomposing the matrix into two in
No,
this.
no. You know, the storage, okay, because it's symmetric matrix, I don't need to store the entire matrix. I only need the lower lower, okay, the diagonal and all the lower elements, or the diagonal and all upper elements, okay. So you can have choose two modes stored in this, okay, this space, okay, lower or upper, okay. So this is the space, okay. Yeah, for the matrix, okay. Yeah.
Okay, I see.
Yeah. Then for the eigenvector, then you need to have the n square, so many elements, okay. But for the A, okay, you only need say the n times n minus 1 over 2, and then plus the n, okay, all the diagonal ones, okay. So that's it, okay, right? Okay, good. So yeah, I think all these terms, okay, yeah, you can find out exactly what it means, okay, from the cookbook and also from the menu of the magma, okay, yeah, yeah. So here, yeah, you can see, okay, all, yeah, all the variables, okay, yeah, they have the comment, okay, on it, okay. So
Okay.
so you can know exactly what it means, okay, yeah.
I see.
So
I
this
see.
is cookbook is very useful, okay, yeah, instead of go through the menus of the magma, okay. The menu of magma even longer, okay, and you will not have such a simple prescription, okay, example, okay. You can just use it directly, okay. Yeah, but you want to know the details, okay, you still have to need to use the magma handbook, okay, the menu, okay, yeah.
I see. Since some of its convention is not
Yeah,
so
yeah,
intuitive, like
yeah,
LO work, LI work, I work.
yeah. Okay, yeah.
Thanks.
So, okay. Now let me go to the code itself, okay. Yeah.
Yes, please.
DSEVD, okay. So this so I make this sample code, okay, actually according to the cookbook, okay, yeah. Here, this is the routine to output the eigenvalue and the eigenvector, okay. And there's a option, okay. I can say, yeah, if option PV, okay, this PV is equal to 1, then I can pin out the eigenvalue and eigenvector.
Excuse
Otherwise,
me.
okay, I can just only pin out the eigenvalues, okay. So this is just a pin out eigenvector and eigenvalue routines, okay.
Sorry.
And yes.
We are still at the
Oh,
documentation.
sorry. Yeah, okay. Yeah, I have to switch to the let me see here. Okay. Oh, okay. Yeah, I have to, yeah. Okay. I have to go to the screening, the, yeah. Okay. Okay. Now you see the monitor, right? Okay. Okay.
Yes. Yes. No. Perfect.
Okay. Now, so this is the first is the routine to output the eigenvalue or eigenvectors or both. Okay. Yeah. So this option is a PV equal 1 is the for eigenvalues, and eigenvectors. Okay. Yeah. So PV is 1, then also pin the eigenvector. Otherwise, only pin the eigenvalues. Okay. Yeah. Okay. So all this part, okay, just the same as the cookbook. Okay. Yeah. Then the specify the matrix size. Okay. Yeah. And then the whether pin out the eigenvectors or not. Okay. And then the so this is the magma manlock at the CPU, and then W1 and W2, and then the A and the R. Okay. So all the memory allocation, okay, actually is on the CPU, but then Magma will just use it, okay, I mean to transfer the data to the GPU, okay, itself, okay. You don't have to worry about how the data is transferred to the GPU, okay. So for example, this is the Magma, okay, and this is the to get the working space size, okay, yeah. And then after getting the working space, okay, once you know the size of the matrix, then you can know what was the working space, okay. Yeah. So and then randomize the matrix, okay, A, okay, and then copy the matrix from A to R, okay. So I have this copy, okay. So this is the generate the random matrix, okay. Yeah. And then the compute the eigenvector, eigenvalues and eigenvector for this UN symmetric matrix. Okay. So this is the magma, okay, yeah, routine. Okay. And then the pin out the time, okay, yeah. So this is timing, okay, is the also using the magma timing routine. Okay. So before and after, okay. So this is GPU time of the get this, and then the code this, okay, to get this the difference between these two time obtained by the magma routine, okay, and then get the GPU time. So yeah, and then output, okay, the eigen, okay, so this is the PV depends on what's the option, okay. So it only pin out the eigenvalue or eigenvector, both, okay, yeah. And then to compare the CPU version, okay. So the CPU, I just call the lab pack, okay, and then call this routine, okay. So you can see, okay, actually LabPack was originally written for Fortran 77, okay, yeah, and you are calling the Fortran routine, okay, from a C code, from a C program, okay, and then yeah, so this is the convention, okay, you have to follow, okay, and then you know the CPU time, okay, and then again, okay, output the eigen value and also optional eigenvectors, okay, yeah, by this routine out eigen, okay, and we can also check the difference in the eigenvalues, okay, yeah, yeah, and then the yeah the error, okay, yeah, here, and then pin out the error, okay, yeah. So and after that, then the feed all these arrays, okay. You can see that the for the lab pack, okay, I use the W2, okay. The matrix is the same, okay, yeah, and then the matrix is the A, okay, yeah, and for the matrix, okay, go to the magma routine is R, okay, and the output, okay, output is the eigenvalues in W1, and then the eigenvectors in the R, okay, okay, so you can see, okay, oh, okay, you can see, okay, here. So W1 is so the input matrix, okay, actually becomes say becomes the eigenvector, okay. So here, so the output here is the R is the eigenvector and W1 is the eigenvalue, okay, you see. So the input, you don't need the extra storing space, okay, for the eigenvector because the input matrix, okay, yeah, can n by n, okay, input matrix, okay, and then that can be after the diagonalization, that space will be used for the store the eigenvectors. Okay. So for the lab pack, okay, the eigenvalue, okay, is in the vector W2, okay, and the A, okay, is the input, the matrix, okay, the original matrix, okay. But then after calling, after exit of this routine, then A will store the eigenvectors, okay. Okay, so there's reason why here pin out, okay, is the eigenvalue here, and then the corresponding eigenvectors here, and then PV is the option whether to pin out the eigenvalue and eigenvector or only the eigenvalue. Okay? Depends on PV is 1 or 0. Okay, yeah. Okay, so so this is the code, the sample code. Okay, but I cannot run the code yet because I think the package has not been completely installed because it takes some time to build a library. Okay, so let me try whether it makes you work. Okay, okay, you see, I could not compile it. Okay, yeah, because the library has not been built yet. Okay, so in this library, Magma library. Okay, so this library, okay, still under development, okay, still being compiled. Okay, after it's completely compiled, then maybe sometime later today, okay, then I can make it, okay, and then run the code again, okay. So the result here is from the test run last year, okay. The input, okay, here the input. For example, 10, okay. So this is the 10 by 10 matrix, okay. Size of matrix 10 by 10, and then pin out the eigenvectors, okay. So so the results output will be here and here, okay. And so actually the last, this is the, yeah. So this is the one in the output of the eigen output data file, okay? So this is a 8192 by 8192 matrix, okay? And then the eigenvector, okay, in this case, 0, okay, so not pinning out any eigenvector, okay? So the results in the, for the eigen magma DAT and also eigen LabPAP DAT, okay? So you can see the eigen LabPAP DAT here. So this is the result, okay? Yeah, you can see, okay, the eigenvalues. Okay, total eigenvalues are 8192. Okay, because the matrix is 8192 by 8192. Okay. Yeah. And the eigenvalue obtained by magma is this. Yeah. There's a typo. MA. Okay. So you can see the eigenvalues are very densely populated. Okay, so from minus to positive. Okay, yeah. And the largest is about 4,000 or so. Okay, yeah. So this is what you expected from a random matrix. Okay, with the elements. Okay, yeah, from a minus 1 or plus 1. Okay, yeah. And if you look at the output, okay, output file 8192, then you can see the difference in the eigenvalues. Okay, yeah, it's only this, so it's quite small. Okay, and the time, GPU time is 26 seconds, and then the CPU time is 62 seconds. Okay, so you can see the CPU and the GPU. Okay, GPU only about 2 times, more than 2 times faster than the CPU. Okay, so yeah, but this is a small matrix. Okay, if you have a larger matrix, okay, then the difference will be larger. Okay, for example, you look at the 16384. Okay, then you can see this. Okay, 176, and then the 480. So this about also 2 point something, but this is the ratio is speed up. Okay, is more. Okay, than the 8192. Okay, so usually the matrix is much larger than this size. Okay, yeah, then the difference between the CPU and GPU will be large. Okay, yeah, yeah, mostly. Okay, you work on a problem with a larger matrix, and also you have to do it many times. Okay, then 1 day and the 2 day will make some difference. Okay, 1 month and the 2 months will make a lot of difference. Okay, 1 year and 2 years makes a very large difference. Okay, so a factor 2. Okay, actually it's quite significant. Okay, yeah. So this is the more than a factor 2. Yeah. Okay, so this is the simplest example of the real and symmetric matrix. The diagonal. Okay, the eigenproblems of the real and symmetric matrix. Okay, let me return to the slides. Okay, and yeah, okay, here. Okay, okay, here. So this is eigen problem of a Hermitian matrix. Okay, so Hermitian matrix is with the complex elements. Okay, complex numbers. Okay, and then the if I take the complex conjugate and do the transpose, okay, that's called adjoint. Okay, then this matrix is the same as itself. Okay, and that's called Hermitian. Okay, so for using the magma, okay, to get this eigen problem, okay, to solve this eigen problem, then I have to allocate the space for the eigenvector. So it's a n, okay. So Hermitian matrix, okay, will give you real eigenvalue, okay. So I only need to allocate the n eigenvalues, okay, because they are all real numbers, okay. Yeah. And then the matrix is complex, okay. So I have the n squared is n2 times 2 because it's a complex, okay. It has a real part and imaginary part. So the storage is doubled, okay. Again, I have to query for the workspace sizes, okay. Okay. And then, yeah, allocate this memory, okay, this work size, okay, memory for the workspace, okay, yeah, and then call this routine, okay. The C, okay, C means is data types the complex, okay, and it's a double, okay. So yeah, so this is a two view double position with two view number with a double position, okay, and this one complex, double complex, okay, yeah. So yeah, then I can go back to the terminal, okay, and to show you the code, okay, in details, okay, yeah. Okay, yeah, okay, and then stop this, and then I have to go to the terminal again. Okay, yeah. So no, just this, okay. Remember. Okay, you can see it. So this routine is the same as before, okay, just for the pin out the eigenvalue and the eigenvectors. Okay. So first I have to create the Hermitian matrix, okay. Yeah. So this is a routine given a matrix, okay. So I have to, yeah, you see for any matrix, okay, I can obtain a Hermitian matrix. Oh, yeah, okay, okay. So what I have to do is just the A, yeah, given any matrix A, okay. Then I get the A plus A dagger, okay, and then divide by 2, okay. So A dagger is the adjoint, okay. So adjoint is the, you take the complex and then take the transpose, okay, that's adjoint, okay. So you get A dagger A divided by 2, okay, and then you get a new matrix, and this new matrix, okay, is Hermitian, okay, yeah. So this operation here is the same as that, okay. Yeah, so I obtain this matrix R, okay, and that is the, yeah. So this is the adjoint, okay. B, okay, is the elements of the matrix A adjoint, okay, of A, okay. So when you add these two mu part together, okay, then you divide by 2, then you get the mu part, okay. So that's why I say, okay, A plus A dagger divide by 2, okay, yeah. So this is exactly this operation. And then, so here, R is the temporary space, okay, and this is the Hermitian matrix obtained from the A, okay, and then I copy this R to A, okay. So both A and R are two matrices. These two matrices are Hermitian. Okay. So this is allocate the space for the magma routine, and also for the space, okay, for the LAPAT, okay, since I have to compare the results of from the magma and also from the LAPAT, okay. So this is the A and R are the space for the matrix, Hermitian matrix, as well as the for the output, okay, for the eigenvector, okay. And W1, W2 are the vector for the eigenvalues, okay. And yeah. Okay, so after calling the routine, then so this is the computer eigenvalue and eigenvectors of a Hermitian n by n matrix. Okay, so this is the calling the magma routine. Okay, and then get the time out and get the time. Okay, and then also to get the output of the eigenvalue and eigenvector. Similarly for the LAPAT, okay, doing the same, and then compare the difference in the eigenvalues. Okay, so yeah, and pin out the difference, and finally free all the memory space. Okay. On the output here is this. Okay, the input, for example, the input is the 8192. Okay, so here I do not pin out the eigenvector. Okay, and let me see the data here. The LAMPAT data. Oh, this actually is only 6 by 6 matrix. Okay, so you can see the eigenvector. Okay, also. Okay, so this is eigenvalue and the eigenvector. Okay, yeah, and also for the this lab member. Okay. Okay, so now let me see whether they have any difference. Okay, yeah. Okay, there's no difference up to the position. Okay, in the format. Okay, you see, this is not very higher precision. Okay, only up to 3 digits. Okay, so yeah, one would not see any difference. Okay, yeah, even for the eigenvalue. Okay, here. Okay, so many digits. Okay, but then yeah, the result from the LAPAT and the magma is the same. Okay, yeah. But if you have a larger matrix, okay, then you will see the difference, okay? Because the numerical error, okay, accumulated, okay, due to different process of the computation, okay, then you may get different errors, okay, at least up to the machine precision, okay, and say 10 to minus 12, okay, or something like that, okay. Such a discrepancy must exist, okay, between the LAPAT and MAGMA, okay, if you have a large matrix, okay, say 8192, okay. Okay. So let me look at the output 8192. Okay. Yeah, I don't have the eigen value and eigenvector, okay, for this. Okay, but the output here, okay, you can see for this for this matrix, okay, with 81 size 8192 by 8192, and the time difference between this is about factor 2. Okay, again, okay, GPU is 2 times faster than the CPU, and the difference in the eigenvalues, okay, is this. Okay, so it's very small. Okay, so this kind of response a little bit slower. Let me see. Okay. Let me try see if it works, okay, for the old code, okay, yeah. But the response seems to be slow, okay. Let me see, okay. SY, yeah, CMD here. Okay. I don't know why the terminal is response so slow. Okay, maybe the network, maybe the machine is very busy in compiling the library of the MAGMA. Okay. CHEEVD. Okay. No. Let me see. I hope I'm not sure I get the spelling correct. Okay. CHEEVD. Okay. Yeah. That's true. CHEEVD. Okay. Let me edit the CMD file again. Okay. CHEEVD. Okay. So this is the direction. Okay. CHEEVD. Okay. Okay. Now let me copy the input to input. Okay. Okay. Now let me see if the code, the old compiler code will work or not. So now it has been submitted. I'm not sure it works because the library, okay, yeah, the old library, okay, was there, but then the old library cannot be compatible with this new version of CUDA. Okay, so the result, okay, yeah, is let me see. Let me see the output. Does it have the output at all? No, it does not have output. Okay, it has an error here. You can see the CUDA. Okay, the condo.err. So okay, you see error while loading the shared library. That means this library cannot open this shared object file. So that means the library has not been completely built yet. Okay, yeah, and this is the old library. Okay, will not work. Okay, yeah, with this new version of the CUDA. Okay, so yeah, okay, so I have to wait until the library is completely built, and then we make the we compile the code again. Okay, and then submit the job. Most likely, okay, I could not do demonstration today, but maybe next time. Okay, yeah, or later you can also try it. Okay, yourself. Okay. Okay. Now let me go back to the slide. Okay. Okay. Let me stop this screen and then switch to another screen. Here. Okay. So these are the two routines. Okay, I'm going to discuss today, and then I go to the example. Okay. So for example, the Laplace operator. Okay. And in that case, okay, if I want to know the eigenvalue or eigenvector of a Laplacian operator, then I need to call the routine, okay, say the DSYEVD, okay, to solve the eigenproblem of real and symmetric matrix, okay. Yeah, this Laplacian, okay, matrix, this can be, yeah, you can see, okay, yeah, this Laplacian we already discussed many times, okay. So consider the few variables, okay, at the site, okay, for simplicity, just on a one-dimensional lattice, okay, on a circular, okay, on a circular lattice with the periodic bounding condition, okay. So so we can easily construct this matrix, okay, yeah. So the periodic bounding condition is just the n-1, okay, is xn is 0, okay, yeah, x yeah, is the from 0 to n-1, okay. So xn-1 is the same as the x-1, okay. So and then xn, okay, is the same as the 0, okay. So you see for the site 0, okay. So the n-1, okay, then it goes back to the n-1, okay. So that's why x-1 is the same as site as the xn-1, okay. And then the xn, okay, yeah, for this side, okay, the forward is the n, okay, but then this side, okay, actually, okay, becomes the 0, okay. So this reason, these 2 points are identified. So this is on the circle. So so with this, that means we have the phi xn plus L equal to the phi x, okay, and that's the periodic boundary condition. Okay. So so this code, okay, so construct the matrix, okay, yeah, with the row, okay, I, and then the column index is this, okay, yeah, this here, okay, here is the X, okay, so the, yeah, J, okay, plus, you see, this is the +1, okay, and then this -1, but then in order to impose the periodic boundary condition, I have to add n mod n, okay, so so with these two operations, then I impose the periodic boundary condition in forward and backward direction. Okay, so and then this is diagonal. Okay, so yeah, this is the -2, and then this is the +1. Okay, yeah, so this is the two matrices. So with this, I will get the say, for example, n equals 6. Okay, then we'll generate a matrix like this. Okay, yeah, here. So this backward, okay, is here. Okay, so the one goes here, and then this one at the side here, the forward position, forward side, okay, is this one. Okay, go back here. Okay, so then I can call this routine, okay, magma DSY-EVD, okay, to obtain the eigenvalues and the eigenvectors of this Laplacian operator, Laplacian matrix. Okay. Another application for this view and to solve the eigenproblem of the view and symmetric matrix, okay, is to solve the Schrödinger equation on a one-dimensional lattice. Okay. Yeah, you see, this can be easily generalized to a high-dimensional lattice. Okay, I just show you the simplest case. Okay, just one dimension, and you can easily generalize it to any dimension. Okay, yeah, and also for any potential. Okay, so this is the eigenproblem. Okay, how to solve the energy eigenvalue. Okay, and also the eigenfunction. Okay. So for one-dimensional lattice, okay, and yeah, so psi x is the wave function at the site, okay, x equals 0 to n-1. Okay. And let me take the simplest example, the phi particle, okay. So with the Vx equals 0, okay. Yeah, in general, you can take any potential you like, okay, and then you solve this numerically, okay. Yeah, once the potential is different, okay, then yeah, the routine, okay, or your code, okay, works for any V, okay, and then you can solve the eigenvalue, eigenproblem, okay. So this V, okay, no need to be a simple, I mean, the simple potential, okay, it could be very complicated form, okay, and then you can still get the eigenvalue and eigenfunctions out of it, okay. So there's the power of the numerical solution, okay. Yeah, if I give you any Vx, okay, not the phi particle, not the linear potential, not the harmonic oscillator, and say extra fourth or even high order, then you cannot get an exact solution at all. Okay, yeah. But numerically, you can always get the eigenvalue and eigenfunction out of it. Okay. So yeah. So this gives you the the solution. Okay, even though there's on a finite lattice. Okay, but you can always make it bigger. Okay, and also take the continuum limit. Okay, then you get the solution. Okay, very well approximate the physical solution. Okay, in the continuum. Okay, yeah. So let me consider the phi particle, okay, with potential V equal to 0. Okay. Then the Laplacian operator, okay, give me this, okay. here I already scaling it, the E over 2m over h bar squared, okay, is the lambda eigenvalue, okay, so yeah. So I already multiplied 2m E over h bar squared, okay, and call this as lambda, okay. So we have to solve this equation, okay. And analytically, okay, I can solve this problem. Say I set psi x equal to exponential I have a x, okay. Yeah, then after I put in x here, psi x here, okay, then I obtain the lambda is the 2 minus 2 cosine alpha, okay. So it's easy to obtain the eigenvalue, okay. Yeah, you try this, okay. Yeah, you put this inside, okay, then you immediately get the eigenvalue, okay. Yeah, because this is the E I have a x minus, and this minus of the E minus I have, okay, this is the E I have, okay, this is E minus I have, okay. So they add together is the 2 cosine alpha, okay. So this the y you have this 2, and these two terms together give you the minus 2 cosine alpha. Okay, so that's a lambda. If I impose the periodic boundary condition, then psi minus 1 equal to psi n minus 1, and psi n equal to psi 0. Okay. So this gives me the alpha n is equal to 2j pi. Okay, j is a integer. Okay, yeah, and this j, the value of j, okay, must be finite because this is just a finite matrix. Okay, it's just an n by n matrix. Okay, you will n size. So this values, okay, j can only be from 0 to n minus 1. Okay, so that I get the alpha j. Okay, so this gives me the all n eigenvalues. Okay, so the eigenvalues is this, and the eigenfunction is this. Okay, so this is the exact solution for the free particle. Okay, yeah, yeah. I think you obtain this in the continuum on a circle, okay, but not on a lattice. Okay, so this is the on the lattice. Okay. So let me put this the wave function. Okay, this is a particle in a box. Okay, so that means the psi x has to be equal to 0 at the end, at the boundary of the box. Okay. So I have, instead of on a circle is with a periodic boundary condition, I have this side of the x minus 1, okay, equal to 0, and then side xn equal to 0. Okay, so further because this is the potential. Okay, that is the box. There's a box. Okay, so the wave function, okay, cannot be extended beyond the box. So the wave function outside must be 0. Okay, so the Hamiltonian, okay, can be generated as this. Okay, so yeah, so this is the periodic boundary condition. Okay, but then for the particle in a box, I just have to impose this to be 0. Okay, outside. Okay, just impose this to 0. Okay, so that means this 0. Okay, yeah. Then so this is the Hamiltonian of a particle in a box. Again, this is, you see, you don't have the 1 here, you have the 0 here, you have the 0 here. Okay, yeah. So you solve this eigen problem, then you get the eigenvalue. okay, and the eigenfunction, okay, for a particle in a box, okay, but this box is a discrete, okay, yeah. So I can solve this also. I can solve this problem analytically, okay, yeah. Yeah, since the boundary, okay, side of the -1 is equal to 0, so the psi x must be a psi function, okay. So you can see, okay, when x equal to -1, then -1 plus 1 is 0. So sine of 0 is 0, okay. So this satisfied. And also sine n equal to 0 will give me this sine of the alpha n plus 1, okay, yeah, n, okay, and x is equal to n, okay. Then this is 0, okay. So the alpha, okay, must be alpha times n plus 1 must be a multiple of the pi, okay. And this multiple, okay, cannot have only have a, because it's an n by n matrix, so you can only have an n values, okay. So this, you have this yeah, n value of alpha, okay, such that, okay, this equation satisfied. So I get the eigenvalues and the eigenvectors for a particle in a box with n sides, okay. Yeah. I can also take the continuum limit, okay, the last spacing a go to 0, okay, and the n number of the size go to infinite, such that, okay, n plus 1 times a equal to l is fixed, okay. So in that limit, okay, then I obtain the lambda, okay. You see, this is the cosine alpha that becomes the alpha j square, okay. Yeah, because the 8, okay, go to 0, okay. So this is the alpha j, okay, becomes the, yeah, cosine, okay, yeah, becomes the small, okay. So this is cosine times it, okay. So you can do an expansion, okay. So this is the cosine theta, okay, alpha, okay, equal to 1 minus 1/2 of the alpha square, okay. So so the 2 is cancelled, and then the 2 times the -2 times the -1/2, okay. So you get 1, okay. So you get the alpha j square, okay. And then in this case, in this, then the number of the eigenvalues will go to infinite, okay. Is quantized, okay. Yeah, discrete, but is infinite, okay, because you have the matrix is the infinite size, okay, n by n matrix, okay, yeah. And the energy, okay, energy here. So you get the alpha is the alpha square. Alpha is equal to e 2me over h bar square, okay. So you just multiply this constant, the proportional constant, okay. Then you get the energy, okay. So the h bar square over 2m times alpha square times lambda j, and is equal to the energy, okay. So you get the energy, okay. So this all you already learned in the course of quantum mechanics, okay. Yeah, for a particle in a box, the eigenvalue and the eigenfunction is this, okay. And the eigenfunction must be 0 on the boundary, okay. Yeah. Okay. Yeah. So this problem, okay, I also have a example code for it, okay. Besides the Schrödinger equation, there are all many problems in classical mechanics also need to solve the eigenproblem. Okay. Yeah. For example, this mass spring system with fixed ends. Okay. So here are the fixed end, and then the spring, and then the mass, okay, and yeah, x0 and x1, they are the displacement of these particles, okay, m1, m2, m3, okay. So, but these particles are all have the same mass, okay. So a chain of particles, each of the mass m, and they connect by springs, and each of the spring constant k, and both end fixed at the wall, okay. Yeah, yeah. Theoretically, okay, and I mean analytically, okay, you can solve this problem with the with the um, with the same m and the same k, okay. But numerically, you can solve this problem for any mass distribution, okay. They can have a different mass, and all the spring constant also can be different, okay. And the numerically, okay, you can still solve the problem, okay. Yeah. So using the Newton's second law, okay, then you can obtain this equations, this set of equations, okay. The for this particle x0, then you have this, and then for the last particle you have this, and then you can see this is the fixed end, okay. So you be reduced to this, and then for the initial here x0, you have this, okay. And then all the particles in between has these three terms, okay. Yeah, if they have different masses, then you can easily generalize it, okay. You don't have you can have the m0, and then mi, and then the n-1, okay. Yeah, and so on. And also similarly for the k, okay, the spring constant can be all different, okay. And you still have this n by n matrix, okay. But this n by n matrix, okay, have many different k and also many different m, okay. Yeah. If the for this simple case with the m and k, okay, all the particles have the same mass, and all spring have the k, then this will become simpler, okay. Yeah. Okay. And then you can have this eigen problem, okay, written as this form, okay. Yeah. And the u, okay, xi can be written as in terms of this ui, and then times this time dependence, okay. And here all the eigen frequency, okay, that means this all particles, okay, oscillating with the same frequency, and that is the eigenfrequency, okay. So if xi, all these particles have a different displacement, but with the same frequency, okay. And in that case, then this system, okay, becomes this, okay. Yeah. So the lambda is the m omega squared over k, okay. Yeah. And so for this n by n matrix, and you can solve the eigen problem, okay, solve for this lambda, okay. And the operator is just the Laplacian, okay. Yeah. So this the matrix again, okay, is this form, okay. Yeah, fixed n, okay. So you can see this problem, okay, essentially the same as the particle in a box, okay. Finally, I will talk about this momentum operator on the one-dimensional space, okay. And this if I want to get the eigenvalue, okay, and eigenfunction, okay, then I have to call this routine CHEVD, okay. First, I have to construct the momentum matrix, okay. So the momentum operator is minus I h bar gradient. Okay, so this is the momentum in the quantum mechanics. Okay, momentum operating in the quantum mechanics. Okay, so can be written as this. Okay, the gradient can be written as the central difference. Okay, so this forward minus backward. Okay, divided by 2. Okay, 2a. Okay, x plus a and x minus a. And then this defines the momentum operator, momentum matrix. Okay, this is the momentum operator, and this is the momentum matrix on a one-dimensional lattice. And if I impose the periodic boundary condition, okay, then I have this. Okay, okay, and then yeah, I can construct the momentum matrix. Okay, as this. Okay, so you can see. Okay, this is the permission matrix, right? Okay, yeah. Yeah, this gradient operator is anti-symmetric. Okay, and then since it's a I multiply to it, so it's a complex. Okay, so when I take the adjoint, okay, then I take the transpose. Okay, then this gradient give you a minus sign, but then the I, okay, also give you a minus sign. So together you get the same, okay, matrix. Okay, so you can see, okay, this is the minus and this is plus. But then you take the complex conjugate and then take the transpose. That's adjoint. Okay, then it's the same. So P deca equal to P. Yeah. So I can also solve this problem analytically. Okay. Yeah. So this equation, okay, yeah, can be written as this. Okay. Yeah. So this just rewrite this equation in this form. Okay. Yeah. And I have the I over half is here. Okay. And then the lambda. Okay. So again, I try this psi x equal to ei alpha x. Okay, so this is the playmate. Okay, for our free particle. Okay, and then I get the lambda is a sine alpha. Okay, so the periodic boundary condition. Okay, would give me the alpha n equal to 2 pi j. Okay, yeah, yeah. So this is easily seen. Okay, yeah, yeah, because the this boundary condition. Okay, periodic boundary condition. Okay. Then yeah, immediately give me this. Okay, and then the alpha j is this. Okay, so the momentum eigenvalue. Okay, when you plug in the alpha j, you get this lambda j, and also the momentum eigenvector. Okay, so this is the yeah yeah for the momentum operator on a one-dimensional lattice. Okay. Yeah, there are many other non-trivial examples, okay, which requires solving the eigenproblem of the Hermitian matrix. Okay, yeah, and you can easily find it, okay, in many physics problems. Yeah. Okay. Yeah. Let me go to the code. Okay. Yeah. Let me go to the code. Go to the switch the screen. Okay. Yeah. And stop this. Go to the terminal. Okay. 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 So there are many subdirections here, and then the, for example, the momentum. Okay. So the output, if I use 1024, 10240, okay. So the, let me see, the eigenvalues, okay, of this momentum output, okay. So this is the 10,241, yeah, 240, okay, yeah, eigenvalues, okay, 10240, okay, eigenvalues, okay. So this are from -1 to +1, I think. Yeah. No. Yeah. Yeah. There's a symmetry. Okay. So -1 to +1. So if you look at the difference between the eigenvalue of the lab pad and then eigenvalue of magma, okay, then you don't see the difference, okay, even though you have how many digits here? Okay. I think there's 11 or 12 digits. Okay, so yeah, so you can look at that. You can see the difference between these two set of eigenvalues. Okay, it's the 10 to the minus 16. Okay, so for this eigen problem, there is yeah, quite accurate. Okay, because this is just the momentum operator. Okay. Now, let me go to this particle in a box. Okay. So for a particle in a box, let me see the output for the matrix of the 8192 size. Okay. So this is almost yeah, around the GPU about two times faster than the CPU. Okay, for such a size of matrix. And the eigen problem here. Let me see the data. Okay, so this is the eigen value and the eigenfunction for this 6x6 matrix. Okay, yeah. And for the code, let me go to code here. Yeah, I'll go in the box. Okay. So this is the eigenvalue, eigenfunction output, and this is a Laplacian matrix. Okay. Yeah. So yeah, so this is the boundary condition to put the boundaries, okay, to be 0. Okay. Yeah. Okay. So this is rather robust, okay, to call the either no matter call the magma or call the lactate, okay. Yeah. So these examples, yeah, give you the show you how to solve the eigen problems, okay, with the lactate and also the acceleration with the magma. Okay. Yeah. Even though these are simple examples, okay, but I think you can easily apply it to any of your problems, okay, in your research, okay, yeah, or in other courses, okay, yeah. Any questions? Hmm? Yeah, I think this library, okay, are quite essential, okay, yeah, for your research, okay, yeah, for your thesis, okay, yeah, because it is a very contribute and tedious, okay, to write high performance and accurate eigensolvers, okay, yeah, for the eigenvalue problem, okay, is the most challenging problem, okay, in linear algebra. Okay. Yeah, solve the eigenproblem is an order more difficult than solving linear system. Okay. These are for the target focus. Okay, the target for the dense matrix. Okay. But most of the problem, okay, actually in physics and engineering are the sparse matrix. Okay. So yeah, the size of the matrix will be much larger than that can be handled by the LabPAT or the magma. Okay. So for the for this magma or LabPAT, okay, you need to have a say this matrix. Okay, you need to know the elements of the matrix. Okay, provided. Yeah. But for the sparse matrix, okay, most of the elements are zero, okay, and you know the which entry, okay, which elements are non-zero, okay. You in most cases you know that, okay, and then you have to generate these non-zero elements, okay, on the fly, okay. So when you do the computation, you generate these elements, okay, or you read this element from the data, okay, yeah, from storage, okay. So that would be a completely different ball game, okay, yeah. You cannot afford the memory, okay, the memory space, the working space, okay, for such a sparse matrix, okay, yeah. So you need some very different approach, okay. And they're similar to what is the Jacobi, for example, the Jacobi algorithm. There's an iterative algorithm, okay, yeah. And for example, this solve a linear system, okay, for a sparse matrix, okay, then one would use for example, this conjugate gradient, okay, yeah. If it's a positive definite matrix, then conjugate gradient, okay, would be the best, or one of the best method. And more recent approach, okay, would be using this multi-grid, okay, yeah, algorithm. Okay. So this beyond what can be tackled by magma or LabPAT. Okay. But for those problems, okay, we don't have any package, okay, for solving such problems. Okay. And mostly depends on which application you are using. Okay. Okay. Okay.
I have two questions. Can I
Yes.
ask?
Yes.
Okay. The first question is that since the four examples provided in the today's slides are all one dimension, so
Yes.
we are encounter a two-dimensional problem or even three-dimension. Can we
Well,
solve it?
easy. Okay. Easy. Okay. You just generate the matrix accordingly. Okay.
Uh-huh,
Okay.
uh-huh.
So, for example, the Laplace equation. Okay. I only give you a two-dimensional lattice. Okay. On the lattice, and then in the problem set. Okay. You do it for 3 dimensions. Okay. Easy to generalize. Okay. You always map this 3-dimensional lattice to 1-dimensional. Okay. Right. Okay. So it's no problem. Okay, this always you can do it. Okay, yeah, yeah. No matter how many dimensions of the lattice, you can always do the mapping to a one dimensional. Okay, and then you see, so yeah, this simple example is sufficient to for generalizing to any other problems. Okay, in any high dimension. Okay,
yeah. But for me, I think it will take some time to formulate how to like from a formula to the matrix form. It will take some time to how to
well,
that.
it takes, I would say it takes only the matrix will be larger, okay, but it will not take more time to do it, okay. For example, if I go back to the, if I do, go back to the Laplace equation, or go back to the, let's see, go the, I think, 2 here. Okay, here. Vector. Okay, we always deal with vector. Okay, yeah. Yeah, you can see, okay, here. This is a 2-dimensional, okay? And I put this 2-dimension, okay, here. X and Y, map to I, okay?
Oops, sorry. So now I only see.
So this is on a 2-dimensional lattice. Oh, okay. Let's see. You don't see this. You don't see it. Okay. Let me. Okay. Oh yeah, it's in the terminal. Okay. Sorry. Let me. Yeah. Okay. Let me go to another. Yes. Here. Okay. Now you see the field on 2D lattice. Okay. Now you are now is in 2-dimensional, right? Okay. You have the X and Y. Okay. And then you map it to the 1-dimensional. This I, okay. So this is always just vector, okay. Okay. Yeah, no matter what, how large high dimension, okay, you can always do the same thing, okay. Yeah, you even have the X, Y, and Z, okay. Okay. Then you can just go generalize this, okay, easily, okay. X, okay, yeah, plus the NX, Y, plus the NX, NY, Z, right? Yeah. So no problem I mean in high dimension, okay. Except now the operator, okay, maybe have a more dependence, okay. For example, the Laplacian, yeah. For example, Laplacian here, okay. Yeah, 2-dimension, you have these terms, okay. You have the X, okay, Y, and then for the 3-dimension, you have the Z plus 1, Z minus 1, and then minus 2, 5, XY. So in that case, you get 6 rather than 4, okay? Laplacian. So you already solve the same problem in the concept of a 3-dimensional lattice, okay?
Yes, that's true.
So that means this reason I say, okay, if I show you how you do it in 1 dimension, then you can do it for any dimension, right? So
my second question is a bit relevant. So regarding the problem involved in tensor, which have a more indices compared to the matrix. So can we also solve
tensor is a little bit trickier. Okay, yeah. So yeah, can we map the tensor to a matrix? Okay, matrix is always just 1 dimension. Okay, tensor. Okay, so for the tensor, then you have to so you have a many-line index. Okay, yeah.
Okay.
But then you can still make a way, okay, to map to the matrix. Okay, yeah. So you just squeeze the components, okay, together, okay, to be 1 component. Okay. So yeah. I think the operator, okay, no matter this operator, how many variable dependence, okay, yeah, you can always do the same trick. Okay, yeah.
Okay, I see. By the way, regarding the last character of the two routines we are talking about, the D
Yes.
actually represent the algorithm of divide and conquer. They use divide and conquer algorithm for.
Oh, okay. D is the divide and conquer. Okay.
Yes.
Okay, great. So you find out the meaning of the last
Yeah,
letter D. Okay.
yeah, from
That's great.
their web page.
On the web page. Okay, good. Okay, good. Thank you for telling us of this. Okay.
Thank you.
Yeah. Let's see. There's some of you, okay, send me a email, okay, have some questions, okay. One of you send the question to the NTU Cool, okay, the mailbox or in NTU Cool, okay, which I do not see. I mean, I do not often go to the NTU mailbox, okay. So you have any questions, you should send it to the TLCHRU at phys.ntu. So that is the email address I always use. Okay, so let me go to here. Okay, yeah. Okay. So in my transparency, okay, yeah. So this is my email address. Okay, you should have a question, you should send it to here, right, and to the NTU Cool. Okay, yeah. For NTU Cool, I may see maybe check the email the box there maybe once per week at most. Okay, yeah. So that's the first thing. Also, some of you have the question about this problem set 3. Okay. Say the question is that, okay, the center of this lattice L by L by L. Okay, and at the center, okay, how can it be at the center? Okay, the question is, okay, if L is say 8, 16, 32, 64. Okay, yeah. Well, you see the boundaries at potential 0. Okay, so the charge, okay, is at the site. Okay, and whether it is a center exactly at the center or not really does not matter. Okay, yeah. So yeah, if you like, okay, you can put it on the say the odd number, okay, and then say L equal to 9, okay, then at the center, okay, and then you have a 4 size in this side and 4 size on that side. Okay, that's fine. Okay, yeah. You see, so this is not a real issue. Okay, if it's you put it, say if the only X size and then the boundaries and the site, okay, yeah, then you can put it, okay, yeah, in at the site in the center, say maybe 4, okay, yeah, if the 1, okay, depend, yeah, okay, you from 0 to 7, okay, so 0, 1, 2, 3, 4, 5, 6, 7, okay, and then the boundary, okay, if the boundary is at the 0 potential, okay, then you can be any point, okay, on the center, okay, you have 2 options, okay, yeah, it doesn't matter, okay, yeah, or you have to extend the boundary, okay, in the to be 0, okay, what the point charge is center, and then you have the four sides on one hand and 4 sides on the other hand, okay, and yeah, but the boundary here, okay, yeah, is at the 0 potential, okay, yeah. So in some sense, okay, that is the same as you identify the the left-hand side as the right-hand side, okay? Yeah. So the point is not the such as one side difference, okay? The point is that when L go to very large, okay, does it go to the Coulomb's law limit? Okay, that's the real question. Okay. Okay. So no matter how you handle the position of the charge, okay, it doesn't matter. Okay. As long as the boundary, okay, is very large, go to very large, and that is zero, and that is the agree with the, say, the Coulomb's law, say 1 over r squared, as r go to infinite, okay, then you go to zero, okay. So that is the boundary condition, okay, and that is the how you can get the potential, okay, and then compare to the exact solution, okay. Some of you, okay, instead of impose it to be zero, then some of you may even impose the what's the value of the exact Coulomb's potential on the boundary, okay, and that's okay, okay, and that's fine, okay. In that case, then you may even get a better agreement, okay, with the okay, yeah, because the boundary, okay, is agrees with the Coulomb's law 1 over r squared, okay. So then in that case, okay, even does not matter, okay, yeah, the center is spaced at one lattice spacing or not, okay, yeah, or you extend or enlarge the lattice, okay, such that you think, okay, it's exactly at the center, okay, yeah. Okay, does it answer your question? Yeah. Any question on this problem?
So, Professor, can I just choose the point nearest to the center as a charge?
Could you say again?
Actually, I typed in the chat to the Google Meet because the internet quality is not very good.
Google Chat.
Yeah.
Okay, could you repeat what you say?
Yeah. So can I choose the point nearest to the center as the place of the point charge?
Yeah, you can put it on the center, sure. Okay, but then you can then after you put a center, then you can extend the side of the lattice, okay, on both sides, the same side, okay, that's fine, okay.
Okay, thank you.
Yeah, so yeah. You see, even though you have the asymmetric, okay, asymmetric, but as long as the size of the lattice getting larger and larger, okay, then this one side of difference, okay, actually does not matter, okay.
Okay.
Yeah. So that means no matter you put L equal 8 or L equal 9 or 64 or 65, okay, that is okay, okay. Yeah. Okay. Is it clear? Yeah. Do you have any question about it? No. Okay. Let's see. About the.
I have a question.
Yes.
If we send you the homework and haven't received any reply, does that mean that the homework is accepted?
No, I haven't get a reply from. I haven't reply you because let's see. I recently in last week, okay, I received several sets of homework. I haven't replied yet. Okay, yeah. Usually I would say, okay, I will receive your homework, okay. But in the last few days, okay, I was very busy, okay, so I haven't had a chance to reply to any of this homework set yet, okay. Yeah, so I will reply to all this email, okay. yeah, at least I will send you a reply say received your homework. Okay, yeah. And some of you asked me, okay, whether he has submitted already 5 problem sets. Okay, ask me whether he should submit more problem sets. Okay, in order to satisfy the requirement. Okay, for example. Okay. In that case, I have to look at all your problem sets. Okay, first. Okay, but yeah, unless okay you are not working, you are not serious in working this problem set. Okay, I think yeah, or your results are completely wrong. Otherwise, okay, yeah, that should fulfill the requirement. They would have said, okay. But I have to look at all your problem sets before I can give you answer, definite answer. Okay, yeah. So for those who have already submitted to V5 problem sets, then I would first would respond to your question, okay, at a highest priority. Okay, yeah. For other people haven't submitted 5 problem sets, then please, okay, yeah, submit your homework as soon as possible. And the deadline is June, is it June 11? I forgot. Okay, let me see. It's June, let me see. I think I have it here. Okay, the deadline is, let me see here. The deadline is okay, here. I should go here. So the deadline is June 11. Okay, so yeah, so you should submit all your problem sets. Okay, before that. Okay. For those of you already submit 5 problem sets, then I would will already tell you long before the June 11. Okay, whether you already satisfied the requirement, the minimum requirement of 5 problem sets. Okay. Yeah.
Okay, thank you.
For the lecture next week, okay. Yeah, I understand some of you may all have a final exam, okay, next week, okay. So for the lecture next week, okay, there is a kind of yeah, you can, if you have a final exam or you are busy in preparing the final exam, then you can just go ahead to skip the lecture. Okay. Yeah. I will be talking about the lattice QCD. Okay. How do I use the GPU in my research on the lattice QCD? Okay. So there is a kind of special talk. Okay. So yeah, so you don't, if you are busy, okay, then you don't have to come. Okay, you don't have to attend the lecture. Okay, that's the message. Okay. So also I try to make the next lecture, okay, yeah, to be more more comprehensible to a general audience. Okay. Yeah. Okay. So any other questions? Okay. Okay, if not, okay. So yeah, see you next week, or you have a nice summer vacation. Okay. Yeah. Okay, bye-bye.
Thank you.